All right, so we have air enters an evaporative cooler at 1 atm, 45 degrees Celsius, 20% relative humidity, and then we've got a volumetric flow rate and whatnot. So yeah, let's see what's going on here. So here's our air coming in and coming in at 1 atm. It's our pressure, P1, P2, our initial temperature, 45 degrees Celsius, and our relative humidity phi is 20% or 0.2. And then we got a volumetric flow rate V dot 1 of 5 meters cubed per minute. And then it leaves with a relative humidity of 90% or 0.9. And then, of course, it does tell us, let's go ahead and bring this over here. So we're injecting, we've got an evaporative cooling process. So we're injecting liquid water, at some temperature here. So, okay. So let's see what we got. So we want to draw the process on our psychrometric chart. Easy enough, I suppose. So this is truly an evaporative cooling process. So evaporative cooling. And we remember that for an evaporative cooling process, our wet bulb temperature is constant. And so that's how we're going to kind of figure out where state 2 is here. So, right, I'm actually going to keep this red here. All right, so what was it at 45? So here's our T1, 45 degrees. And 20% relative humidity, so that's this guy right here. So right there's our state 1. Let's make this actually black. Spot right there. Okay. And we've got here we go. Got a constant wet bulb temperature to a relative humidity of 90%. So sure I draw that correctly. It looks like right there. And I could draw a line in between those if I really wanted to show it's going at a constant wet bulb temperature. But there's state 1 and state 2. Let's make that a little fatter. So state 1, state 2. And then I could read off whatever properties I needed. So I've done the first thing, right? I've drawn it on a psychrometric chart. And then the next thing I'm supposed to do is figure out, psychrometric chart, done. Check. And then part B, supposed to find the mass flow rate of the atmospheric air entering the evaporative cooler in kilograms per minute. So it's atmospheric air. We're talking about the dry air and the water vapor together. So M dot 1. And so, all right, well, let's do a mass balance. And we'll do it on the air and on the water. So with the air, the only thing that it's going to tell me is M dot A is constant, right? I've got one inlet, one outlet for that dry air. And then for my water vapor, my water vapor, it's going to tell me, all right, I've got two inlets for the water vapor, so M dot V1 plus my M dot of that injected water equals M dot 2. And then I could rearrange that, right? This M dot W, he's going to be equal to M dot V2 minus M dot V1. Maybe I put that in terms of M dot A. So we've done this guy before. And that's still not there. However, I also can say, well, if I were looking at the mass of a mixture, it would be the sum of the components. And same thing for that mass flow rate. So I've got contribution from the dry air component plus the water vapor. And I know the water vapor mass flow rate is going to be different at the inlet versus the outlet. So I need to put a little subscript 1 there. And then maybe I'll put this M dot A on the outside. And then this would be 1 plus m dot v1 over m dot a, which would just be the specific humidity at 1. Perfect. All right. So there's a couple of things that I do need to figure out here. I need to figure out the mass flow rate of the air. So let's do that. And we're going to relate that, I think, probably to that volumetric flow rate. That seems like a good thing to do. So volumetric flow rate V dot 1. We've done this before where we said, okay, well, Dalton's model said that the volume of the components in the mixture are the same. So let's kind of extend that to our volumetric flow rates. So this would be the same as V dot A1, which would be the same thing as M dot A times the specific volume at state 1. All right. And so I can get my M dot A. This one's going to be V dot 1 over that specific volume at state 1. So it's going to be 5 meters cubed per minute over whatever that specific enthalpy, or I'm sorry, the specific humidity is at state 1. And I can probably pull that off. So let's see. About 0.012 looks like. So 0.012. So that M dot A is going to be, oh boy, let's see. So the M dot A is going to be 5. Sure, I've got this. Oh, oh my goodness, my goodness, my goodness, my goodness. Ridiculous. That's the specific humidity, not my specific volume. My goodness. So our specific volumes are the ones like that. That's 0.9. This is 0.95. So it looks like each one of these guys. Oops. I'm gonna sneeze. Okay, I was trying not to hurt anybody's eardrums there. All right, so there's 0.9, 0.95. So each one of these is 1, 2, 3, 4. All right, so that's 0.9, 0.91, 0.92. So it looks like we're really close to 0.92. I think I could read with the accuracy to 0.918 on the solution. All right, so 0.918. Sorry about that, guys. So meters cubed per kilogram. So my M dot A ends up being 5.4466. So 5.466. And then that would be in kilograms per minute. And then, of course, this guy, which I was trying to use before, that one's that 0.012. All right, and so our final answer for our mass flow rate, let's see what he ends up being, 5.51. So 5.51, and it's kilograms per minute. Perfect. And then the very last thing is asking for the mass flow rate of that water injected into the evaporative cooling, into the evaporative cooler. So what we're really looking for is this guy up here, and we already got that with our mass balance on the water. And I've really got everything that we need because I've got my M dot A, this guy right here. I've got my specific volume at, or my specific humidity at 1. I do need the specific humidity at 2, so let's go ahead and get that guy. So it's like about 0.02. Yeah, I thought it was maybe 0.019. Pretty close. I'll use the 0.0. Let's see. Yeah. I don't know. It's kind of hard to tell, isn't it? Maybe it is a little lower. Eh. On the solution online, I put 0.019. I don't know. Oops. I look at it. Actually, I think maybe it is. I think maybe it is actually this one right there. It would really be like 0.0195. let's call it that, 0.0195. Again, as long as you're in the ballpark, it's fine. So let's calculate it with the 0.0195. So that guy, say that guy, and let's see. All right, so about 0.04 and change. So if we had used 0.02, we would have got 0.0381, but this is fine. This is good enough for government work. 0.04, and it's kilograms per minute. So that's our m.w, and that's part C. All right. Thanks for watching. Let me know if you have any questions.